when the Large Hadron Collider at CERN first powered up, slamming protons together at mind-boggling speeds, it wasn't just about discovering new particles. Scientists were chasing something straight out of science fiction. Tiny black holes born in the quantum realm. These aren't the monstrous void swallowing stars in deep space. They are microscopic marvels, flickering into existence for a split second before vanishing in a burst of energy. Imagine unlocking the secrets of gravity, extra dimensions, and the fabric of reality itself, all from a lab buried under the Swiss-French border. This pursuit has captivated physicists, sparked wild debates, and even stirred up fears of doomsday scenarios. But let's dive into what really went down, step by step, as we unravel the story of humanity's bold hunt for these elusive quantum beasts. Picture this: protons racing around a 27 km ring accelerated to nearly the speed of light, then smashed head-on with the force of a freight train compressed into a pinpoint. That's the LHC in action, the world's most powerful particle accelerator. Back in the early 2000s, as plans for the collider took shape, theorists proposed a wild idea. What if our universe has more than the three spatial dimensions we know? What if gravity leaks into hidden realms, making it possible to create black holes right here on Earth? Models like the one from Nima Irani Hamed, Savas Dimopoulos, and Jihad Valley, often called the ADD model, suggested that extra dimensions could lower the energy barrier for black hole formation. Instead of needing the mass of a mountain squeezed into an atom, you might pull it off with just a few trillion electron volts or TeV. That's exactly the ballpark the LHC operates in, peaking at 13 kV per collision. Then there's the Randall-Sundrum model, crafted by Lisa Randall and Raman Sundrum. It paints a picture of our reality as a brain, a three-dimensional slice in a warped five-dimensional space. Gravity gets amplified in this setup, again making many black holes feasible. These theories weren't just idle speculation. They aimed to solve the hierarchy problem, the puzzle of why gravity is so feeble compared to forces like electromagnetism. If extra dimensions exist, gravity's apparent weakness makes sense. It's diluted across unseen spaces. So, when the LHC fired up in 2008, after years of construction and billions in funding, the stage was set for a groundbreaking experiment. Scientists weren't content with theory. They wanted proof, something tangible. From the debris of those proton crashes, enter the detectors. Massive, multi-layered behemoths like CMS and Atlas, each the size of a cathedral and packed with sensors finer than a human hair. CMS, for compact muon solenoid, weighs as much as the Eiffel Tower and tracks particles with exquisite precision. Atlas, its rival sibling, does the same on an even grander scale. These machines capture the aftermath of collisions, sprays of quarks, gluons, electrons, and more exotic bits. For black holes, the signature would be unique, a sudden evaporation via Hawking radiation, named after Stephen Hawking's revolutionary 1970s insight. Hawking showed that black holes aren't eternal prisons. They leak energy through quantum effects at their event horizon. For a tiny black hole, this isn't a slow drip, it's an explosion. In less than a billionth of a trillionth of a second, it would radiate away, spitting out particles in all directions. What would that look like? A high multiplicity event. Dozens of particles jetting out symmetrically, with energies hinting at something beyond the standard model. Researchers pored over data from millions of collisions using Monte Carlo simulations, computer-generated mock-ups, to predict what black hole decay might resemble. They scanned invariant mass spectra, plotting how particle energies clustered, hunting for bumps or anomalies that screamed black hole. Early runs at 7 TeV yielded nothing definitive, but they set limits. No black holes below 3.5 to 4.5 TeV in certain models. As the LHC ramped up to 13 TeV, the search is intensified. Atlas analyzed electron-jet and one-jet pairs, sifting through 140 inverse femtobars of data, a measure of collision abundance that boggles the mind. Yet after all that, the results were silence. No smoking gun. The CMS team excluded black holes up to higher masses, and Atlas pushed it further. 9.2 for ADD, 6.8 TeV. For Randall Sundrum. These aren't Failures, they're victories in disguise. Science thrives on constraints. The lack of black holes tightens the screws on extra-dimensional theories. Maybe the extra spaces are tinier than thought. Or gravity's fundamental scale is loftier. Perhaps these models need tweaking or entirely new ideas. It's like mapping uncharted territory by noting where the dragons aren't. And remember, the LHC hasn't exhausted its potential. It's only probed a fraction of possible energies. Of course, the idea of manufacturing black holes freaked people out. Headlines screamed about Earth swallowing voids. Lawsuits flew and conspiracy theories exploded online. CERN faced a PR nightmare, but they tackled it head-on with rigorous safety reviews. The key argument: nature's been doing this forever. Cosmic rays, high-energy particles from supernovas and beyond, hammer Earth's atmosphere with punches up to 10 to the power of 20 eV, dwarfing the LHC's output. If many black holes were dangerous at collider energies, our planet would have been Swiss cheese ego. Plus, Hawking radiation ensures instant evaporation. A micro black hole couldn't gobble matter. It would fizzle out faster than you can blink. Its temperature soaring to 10 the power of 17 Kelvin, hotter than anything imaginable. Even if hypothetically a stable one formed, which theory says is impossible, it would be harmless, too small to interact much. It had drift through Earth like a ghost, acre wing, mass slower than a snowball in hell. Experts like John Ellis from CERN crunched the numbers, and independent panels from the European Commission to US physicists signed off. The LHC Safety Assessment Group declared it safer than crossing the street. Public education helped 2 blogs, videos, tours, demystifying the science. It turned fear into fascination, drawing millions to ponder the cosmos. Zooming in on Hawking's contribution, it's a cornerstone. Before him, black holes were seen as one-way streets. Stuff goes in, nothing comes out. But quantum mechanics demands pairs of particles pop in and out of existence near the horizon. One falls in, the other escapes, siphoning energy from the whole. For stellar black holes, this radiation is negligible, but scale it down to quantum size and boom, rapid demise. The process yields photons, leptons, hadrons in a democratic spray. Unlike biased standard model decays, detecting that would confirm quantum gravity, bridging Einstein's relativity with the quantum world, a holy grail of physics. The implications ripple outward. If black holes popped up, it'd scream extra dimensions. The AD model envisions large extra dimensions where gravity spreads thin, explaining its feebleness. Randall-Sundrum warps space so gravity concentrates near our brain, solving hierarchies without huge extras. CERNs null results nibble at these extra dimensions, if real, must curl tighter or warp differently. This feeds into string theory where dimensions abound and loop. Quantum gravity, another unification contender. It's not just abstract. Understanding gravity at quantum scales could crack dark matter, dark energy, even the Big Bang's infancy. To spot these ghosts, CERN's tech is wizardry. Silicon trackers map particle paths with micron accuracy. Calorimeters absorb energy bursts, converting them to light signals. Muon chambers catch the slippery particles that pierce everything else. Data floods in at pabytes per second, filtered by AI algorithms spotting anomalies. Machine learning sifts the haystack. Neural nets trained on simulated black hole events flag suspects amid QCD backgrounds, the mundane proton fragments. It's a needle in haystack game, but with supercomputers and global grids. They've analyzed billions of events. Looking ahead, the adventure is far from over. The high luminosity LHC slated for 2029 will crank up collisions tenfold, amassing data faster than ever. That means probing rarer events, higher masses, maybe up to 50 keV with future tweaks. Beyond that looms the future circular collider, a 100 km beast eyeing 100 keV energies. It could nail or bury these theories for good. New detectors promise sharper eyes, better timing, radiation hard sensors, quantum tech for precision. Theorists refine signatures to perhaps asymmetric decays or linked phenomena like gravitons. This quest reshapes physics broadly. Techniques born here boost Higgs studies, neutrino hunts, even medical imaging, particle Tech spun off into cancer therapy via proton beams. Safety probes deepened. Cosmic ray knowledge, revealing atmospheric cascades mimicking LHC events. Null results prune the theory. Tree, sparking innovations. Modified. Extra dimensions, composite gravity. Axie, collaboration span fields. Particle pros team with cosmologists on universe origins. String theorists on multiverse. It's interdisciplinary magic. Fostering insights like how black holes might seed galaxies or evaporate. Primordial relics. Even without black holes, the LHC's legacy shines. It confirmed the Higgs boson in 2012, completing the Standard Model while exposing its cracks. No supersymmetry. Yet, no dark matter particles. The black hole search exemplifies bold inquiry. Hypothesize, test, refine. It inspires generations. From school kids building accelerators with magnets to pros. Pushing frontiers. Public engagement surges. CERN's open days draw crowds. Online forums buzz with debates. It's democratized science showing how curiosity drives progress. As energies climb, who knows what awaits? A black hole flicker could rewrite textbooks, unveiling hidden realms. Or continued absence might pivot us to new paradigms, like holography where our 3D world projects from a 2D boundary. Either way, it's thrilling. We're not passive observers but active probers, tweaking reality's dials. The universe hides secrets, but with tools like the LHC, we're cracking the code, collision by collision, reflecting deeper. This endeavor mirrors human spirit, daring to question, engineer impossibles, confront fears. From ancient stargazers to modern colliders, we've evolved from myths to math, wonders to wisdom. Microblack holes may remain elusive, but the chase illuminates gravity's mysteries, quantum quirks, dimensional dances. It's a reminder that science isn't cold facts, but a passionate pursuit blending intellect with imagination. In the end, CERN saga isn't just about particles. It's about us probing existence, seeking unity in diversity. As detectors hum and data flows, the next breakthrough beckons, promising revelations that could redefine everything. Stay tuned. The universe's story is still unfolding, one smash at a time.